me when you did. Perfect. Hey guys, all right, so happy snow day. Now, something we need to talk about is the fact that buffers are going to be a major component of the acid-base equilibrium, and it's one of the most challenging components as well. So today I'm going to give you kind of a crash course on buffers and how it pertains to titrations, which we learned about already. So here's buffers in a nutshell. First thing you want to do is recognize how buffers relate to the titration curve. So first let me draw a titration curve real quick. So titration curve, remember, is going to be the pH of whatever the original species you're looking at is compared to the amount of a strong either acid or base being added. In this case, we're going to be titrating a weak acid with a strong base. Let's say sodium hydroxide, for example. So if we start with a weak acid versus a strong base, what we're going to do is we're initially going to see a dramatic increase in the pH right off the bat. Then what's going to happen, and this is kind of the signature of a weak acid titration, is that we're going to flatten out for a period of time, followed by a dramatic increase where at the end of the titration curve, it looks very similar to how a normal strong acid, strong base titration curve would look. But there's this weird period here, this weird area where the pH seemingly doesn't change. Now, there's a reason for that, and that's because this is where we are buffering. We call this the buffer zone. And the buffer zone of any weak acid or of any weak base is the area where a change in pH is resisted even though we're still adding a strong species of the other type, right? So in this case, we're looking at a weak acid, and somehow that weak acid is not changing pH even though we're adding a strong base. So what's going on? Let's relate it to equilibrium. We now have learned that the weak acids and weak bases are always in stages of equilibrium. So the equilibrium of a weak acid in this case is going to be where this could, remember, be either H plus or H3O plus hydronium. So here's what's going on, constantly at equilibrium. Now, by adding a strong base to this situation, we look at this and we say, well, Le Chatelier doesn't matter because it's not adding any common ion. However, much like we saw when we did the lab where we pulled chlorine ions out of solution, that's effectively what's going to happen by adding a strong base. Whereas instead of pulling chlorine ions out of solution, in this case, we're pulling hydronium ions out of solution. So what's actually happening is by adding a strong base, that base is immediately going to react with this hydronium, H3O plus, to form water. So that strong base is going to react with hydronium, and it's going to pull it out to form water. What that is going to do is shift the reaction to the right. The reason that adding the strong base is not going to affect the pH during the buffering zone is because every time it reacts with this H3O+, we can shift the reaction to the right. So what's going to happen initially is we're going to have a very dramatic increase in pH due to the initial addition of strong base. That is going to be a quick change, but then the most important feature is this. This is where we call our buffering zone, because this is where the buffer, the weak acid, is going to have the greatest resistance to change of pH. Why? Well, as you add hydronium ions to solution by shifting it over to the right, we then add more base, which then react with those hydroniums, shifting it further to the right. Now, because hydronium is what's going to actually impact our pH, what's not going to impact the pH is this HA, because remember, the pH is about the loose or free H plus ions. If it's still in the form of HA, that means it's still associated with that weak base conjugate, And so what's going to happen is we're actually going to see this have no impact on the pH. As we shift it to the right, we're essentially using a hydroxide to suck out any of these hydroniums that happen. So what's going to happen is we're going to very slowly change pH right as we're shifting it to the right. So this is essentially caused by the Le Chatelier principle. Now, there's going to be a point where that shift stops. And the point that is going to happen is when you run out of HA. As we start to run out of the weak acid to react with, that base that's being added is going to overwhelm and start to cause the pH to dramatically increase. It's going to go up very quickly at that point. So what's happening, first of all, is the weak acid is going to shift to the right as this H3O plus is being removed from the solution by the strong base being added. That's our buffering zone. So where is a weak acid going to be the best buffer? The key to a buffer is that it resists change of pH in either direction. What that means is whether you're adding a weak base or a strong base to a weak acid or a strong acid to a weak base, in every case we're going to resist the change in pH. So the point at which that is going to happen best is when we can shift in either direction to a maximum degree. Because if we add hydroxide, we're going to shift to the right. However, if we add hydronium, say we add a strong acid, now we're going to shift the reaction to the left. And we have this A minus, which can actually absorb, if you will, any extra hydronium ions. So what we can do is by shifting either way. Well, in what situation can we shift maximally in either direction? The answer is when we have equal concentrations of weak acid and its conjugate base. If we have equal concentrations of weak acid and conjugate base, then we know that we can shift in either direction as much as possible. That is the center of our titration buffer zone. Right in the middle is where we have equal concentrations of our hydronium ion, or our HA, our weak acid, and of our A minus, our conjugate base. That's the center point of our buffer zone. In order to do this, there's going to be an equation that we're going to use. And that's going to be that pH is equal to pKa plus the log of our weak base conjugate over HA. Now, what that is going to tell us is when these two are equal, log of 1 is 0. Which means pH is equal to pKa at the center point of any buffering zone. So we know where a weak acid or a weak base is going to be the best buffer because that pKa will be equal to its pH. Okay? At that point, we know that it's in its best buffering zone. And within plus or minus 1 of that in pH terms. So let's say a buffering zone's at pH 4. That means it will be an effective buffer from pH 3 all the way through pH 5. Right? And the reason for that is because of the activity of this equilibrium, shifting left or right. So when pH and pKa are equal, that means your concentration of weak acid and weak acid conjugate are equal. That's important. As we shift further to one side or the other, this will become more skewed. And so it's important to realize that when you're looking at buffers, there are a lot of possibilities. And here's what we need to look at. With weak acid and weak base buffers, you need to be able to reference the help sheet that I gave you. That help sheet is going to tell you what's going to happen before the buffering zone, in the buffering zone, before the neutral point, or the titration point, the end point, and after. Be aware. Strong acids and strong bases cannot act as buffers because of the fact that they do not show this equilibrium reaction. They are not in equilibrium with each other, the weak acid and its conjugate base, because its conjugate base is, or the strong acid and its conjugate base, because the strong acid and its conjugate, the conjugate in that case is going to be pathetic. With a strong base, its conjugate is going to be a pathetic acid. So they don't show this equilibrium, all right? Because the pathetic conjugates cannot accept or give hydrogen ions in order to make it shift back to the other side. It's one directional, it's permanent. So the keys to buffers, this is what you need to know with buffers. All right, and this is something you're going to have to do in terms of your own practice problems today. Number one, recognizing where a buffer is going to be most effective. Two, recognizing the fact that buffers are created by equal amounts of weak acid and its weak base conjugate, or weak base and its weak acid conjugate. There are a couple of ways we can get to equal concentrations of each. Way number one is we can take a weak acid and titrate it halfway. That means we go halfway to the titration point. So in other words, if it takes 10 milliliters of strong base to neutralize that acid, that means 5 milliliters of the strong base would get it halfway. That's our buffering zone. Halfway to the titration point is pKa. Second way we can do it is by adding a weak acid and its conjugate base as a salt. So if I took acetic acid and I added sodium acetate in equal molarities, that would create a buffer as well. All right? The next thing you need to do is predict how the addition of a strong acid or a strong base to a buffer solution would impact that buffer solution. You need to reference your formula sheet for this because these formulas are on your formula sheet. Finally, what you're going to need to be able to do is take a buffer solution and predict not just the change in pH, but also how it's going to change over time given multiple different concentrations of strong acid or strong base being added, which means you need to use the help sheet that I gave you because it'll tell you when to use which equations. Because once you leave this buffer zone, it behaves very differently. Once you pass this titration point, it essentially just behaves like you're purely a strong base. Because at that point, the strong base has overwhelmed completely the strong acid and weak acid. But here's the key. If you're somewhere else, we have to account for the fact that there's going to be a weak base conjugate or a weak acid conjugate in water, and those will actually impact the pH to some extent. If you have a weak base in water, it will react with the water to increase the concentration of hydroxide. If you have a weak acid in water, it will react with the water to increase the concentration of hydronium ions. You have to account for those when you're looking at buffers. So that's your crash course in buffers. Now, you need to make sure that today, during this wonderful snow day that we have, and if we have one tomorrow, what you need to be able to do is identify buffer problems, solve buffer problems, and in order to do this, you need to make sure you understand the basics of buffers. All right, I have posted a help file on the website that you can utilize as needed. All right, this is a really helpful help file. It's from the NCBI, and they do a great job going through buffers. I'm also going to post a couple of potential help videos that you can use. The key is, you guys, buffers are one of the hardest things in equilibria, in acid-base equilibria, but they're also one of the most critical because they are of absolute utmost biological importance, and the AP loves talking about it for that reason. All right, enjoy the snow day. Make sure you're getting work done. Work on your pre-assessment corrections. All right, and I'll see you guys when we get back in school. All right. Sorry, I meant to lock the door. All right, let me reset. Oh, you're fine, Justin. You didn't know. I meant to lock the door. All right, starting. Where did I start? Where was I? Okay.